Okay, so today we'll look at this dynamic voltage and frequency scaling, chapter 9. Okay, low power methodology manual. I hope you guys have gone through that chapter. Um, we'll basically, the idea here is that you know frequency as a function of voltage. Um, you have a you have a pretty large range out here. So this is just a cartoon sketch I have drawn where um, as you drop the voltage, the frequency also drops, kind of somewhat linearly in the beginning, but then below a certain voltage, it just starts dropping dramatically when you start hitting close to the threshold voltage. And there is a minimum voltage of operation below which the circuit will not work. Now, usually these voltage ranges out here are very low near threshold voltage, and normally, the commercial chips so far right now don't go into that voltage range. But later on in the course, we'll kind of look at what is required to operate circuits down at those voltages, near threshold voltages. Is it interesting? What are the issues and so on? But for now, let's worry about this range out here, where you can still have, when you drop your voltage from say 300, some max operating voltage to maybe about half of that voltage. That is kind of a range which is reasonable to have your chips run at, and you can get your voltage also to change by about 400 to 500 millivolts, from the max voltage to the min voltage. So that gives you a lot of voltage headroom to play around with to reduce your power as well as energy consumption. Now the thing is that this frequency to voltage mapping, it is really a function of, that mapping is different for every chip. Each chip is unique. So there will be a spread out here. So spread is due to the variations in the process, the temperature. I should not put V out here. It's just it should be basically process temperature spreads. Okay, because voltage is anyway the parameter which we are using out here. So now the thing is that what these two curves are kind of capturing the limits in some sense for a particular design for a particular process. That means when you take randomly some chips from that particular factory which makes those across a period of time, their frequency to voltage mapping will lie between these curves. So these curves are kind of the extremity. You can say, you have to kind of give some number, maybe 99.5% of the chips will lie within this curve, or some such number you have to give to quantify that. Okay, with that probability, a very high probability, you will be within this bounds out here. So this frequency to voltage mapping is very important when we talk of dynamic voltage to frequency scaling. What is the idea of dynamic voltage to frequency scaling? The idea here is that you have the requirements, the frequency requirements can change with time. You don't always have to operate at one fixed frequency. For example, now the laptop, this particular laptop which I am using, is not really doing any computation. Okay, it's just some graphics is basically operating to show the PowerPoint slide. The core of the chip is not really doing much. So the system can actually reduce the frequency of operation of the core of the chip and reduce the power consumption. So that is what is called dynamic frequency scaling. That means as the system is running, there is some intelligence in the system to monitor the system. And what is that intelligence? How should it work? That is a separate topic. We'll kind of look at what could be possible ways by which you can figure out what should be the frequency at which to operate. One could be the kind of applications running, right? For example, right now, if you know that you are having PowerPoint and there is not much input keystrokes coming in, then it's really kind of not doing much computation. So they could, that is a simple way. Like that, there could be multiple different ways by which the system can sense or guess what is the computing requirements, and then based on that, it can say this. I can reduce the frequency to so much. Okay, because I'm kind of expecting not much to happen. So that is what is called dynamic frequency scaling. So you are kind of dynamically adjusting the frequency. As we saw the other day, when we reduce the frequency, the power consumption comes down, the dynamic power consumption, because dynamic power consumption is half alpha CV square F. Alpha is the activity factor, CV square F. So as I reduce F, dynamic power will come down linearly. Of course, if I reduce F, I can also reduce voltage, because what this graph is showing me is that if I reduce F, I should be able to operate at a lower voltage. For some region, F to V is kind of a linear relationship. So for that particular region, when F scales down by some factor, V can also scale down by a proportional factor. So the overall savings in power will be cubic, because I have V square times F, right? So I have a cubic relationship. Also, of course, the energy comes down, because energy consumption, dynamic energy is half alpha CV square. So as I reduce voltage, energy comes down, which is energy per operation also comes down. So this is very important for battery operated systems. Say I was not connected to the power here and it is running off the internal battery, then I can prolong the lifetime of the battery. Now the question is, when I reduce my frequency, okay, my system says that, look, you don't need to run at 2.4 gigahertz, you can run at 1 gigahertz, okay, for the next so many milliseconds or seconds or whatever. So then that means I can reduce the voltage. But what should the voltage be? At 2.4 gigahertz, maybe I'm running at the max specified voltage, which is 1.2 volts for my processor core. At 1 gigahertz, what should the voltage be? I can determine that voltage by looking at this frequency to voltage curve, right? So if this corresponds to 2.4 gigahertz, okay, so now when I spec my chip, right, this is my slowest chip, this is my fastest chip. Remember, we are talking of chips being fabricated, right? You have millions and millions of chips formed, right? So there'll be a spread in their performance characteristics. So there is going to be a spread in their frequency to voltage curve. So when we spec a chip, commercially you want to sell a chip and say it runs at, if you want to make it run at this volt frequency and then you have to use this voltage. What should that voltage be? That voltage will be the lower bound out here. I mean, for that frequency, you have to look at the voltage which is given by this curve, the lowest curve out here. These are the slowest chips, right? Because if I use this voltage and the chip corresponding to the lower bound, this curve works there, then any other chip for that voltage will also work at that frequency. In fact, it has capability to run faster. But we are just saying, look, if you use that minimum voltage. So you can use this table or this curve or this mapping, which is at the lower bound of the F to V spread. And you say that is I'm going to use that as my table or a mapping. So how do you find that table? How do you find this curve F to V? I mean, when I'm using the word table, the reason I'm saying that is that this curve F to V is easily stored as a table, right? Where you just take a few frequency points. You don't need that much. You have max frequency, maybe 3/4. You have a few discrete to half, right? Maybe 5 points or something. And that means you're taking 5 such points along this curve and corresponding to that 5 such voltage points. That could be a F to V table, which is stored somewhere.
But that way is the not best way. Like you are operating using the faster chip at a slower frequency. So that is not the best possible.
Correct. So the question being said here is that if you use the conservative lower bound, then you're leaving performance on the table for the fast chips. Because out here, there is one chip or a very small number of chips which are determining, they are the weak links, right? They are kind of holding hostage all the other chips in some sense. So I'm promising only say 2.4 gigahertz, whereas a lot of chips would be able to run much faster, and there will be few outliers which will run even faster, right? So how do you what do you do? How do you deal with that? That is where the adaptive voltage scaling comes. We'll just have a look at that. Before that, let's look at dynamic voltage scaling. So now that you have this mapping of frequency to voltage, if there is any particular frequency target, say this is the frequency target, new target, I'm running at this F max. Now I'm saying, okay, for this phase, go at F target, which is lower than F max. Then, if I had a way of controlling the voltage, what I'll do is instead of running at this voltage, the max voltage, I'll push down the voltage to a voltage corresponding to this out here. So I get this much savings, additional savings in power because I have scaled the voltage. So this is called dynamic voltage scaling, because I'm also adjusting the voltage dynamically along with adjusting the frequency. So it's called dynamic voltage and frequency scaling, DVFS. Now in addition, your particular chip, maybe the chip specifically, in a particular instance of the chip might be maybe somewhere sitting out here. Its F2V curve maybe somewhere in between these two. If I knew that this is the condition of the chip, it's actually a better chip than the worst case chip, then I can squeeze out some more. I can move the voltage even lower. I can adapt my voltage to the specific process condition of the chip. That is called adaptive voltage scale. Right? Similarly, for a given voltage, that particular chip I can run at a higher frequency than what you would say. So that is called what is called overclocking. You might have seen where you can actually take your PCs and make them run faster than what they are actually spec'd at. That is because there is this kind of a headroom there, so you can push it up. How much you can push it up? We have to do trial by error. You have to see, at which frequency it will work and fail. But you can push it up. If you're lucky, you might get a chip which is from the other end, and you might really be able to push it a lot. One thing you have to remember is that when you really push it, you're going to burn a lot more power, and rest of the system is it been designed to handle that power dissipation. You have to be careful with that. You should not bring down your system because you are overclocked it, because rest of the thing has not been designed to handle that kind of higher power dissipation and higher currents. Okay, so that is why the manufacturer will not give you any warranties. But you can do it at your own risk. So this is what is called adaptive voltage scaling, but today we will focus first on dynamic voltage scaling, and next class we will come back and look at adaptive voltage scaling. Because this problem of knowing where your chip actually is, that is a tricky problem. How do you figure out what is your chip?
How do we get a curve?
This curve is obtained by basically timing analysis. The most accurate way would be to actually, if you had good models, so the transistor models are good, which is usually the case now for digital design, you can use circuit simulation to get this curve. You run Spectre or HSpice or Eldo, any of these circuit simulation tools. You take your circuit and you simulate it and find the delay of the critical paths. Okay, the problem is there could be many critical paths, and that is where this kind of analysis becomes difficult to F2V, right? So this is a kind of a challenging. If it was a small circuit, then you can easily find this F2V curve by just running at different voltages, just seeing what is the max speed at which it runs. But if these are big circuits and part of SOCs, then you have many timing paths and you have to do static timing analysis. That means when you do that, the timing models or the cells, the timing tools uses timing models for the cells you are using, and those models are not available at these different voltages, then you can't do that. Then you have to come back and do some kind of circuit based simulations. Circuit simulation will work because the transistor models will work across pretty large range of voltages, but it can be a tricky thing to get this curve. Right? It requires a lot of characterization and analysis. So as we saw, as you reduce the frequency, the power does come down, but in addition, if you do a voltage, frequency and voltage are scaled, you can get much more reduction in power than the linear reduction in frequency. Okay, so that is why you would like to do dynamic voltage and frequency scaling. And nowadays it's kind of easy to adjust the voltage. You have voltage regulators and power supplies which you can digitally control, and you can say give me this new voltage and it will kind of give you that voltage. So how does this system look, the DVFS system? The DVFS system basically, so here is an example system where what you have is you have a system on chip SOC, and there are two domains in this system. This is the block, CPU block, whose voltage is controlled dynamically, okay, whose voltage and frequency, which is under DVFS control. The rest of the system is not under DVFS control. So that is why you see there are two power supplies to this chip. This is a fixed power supply which supplies only to the remaining portion, which is at running off a fixed voltage and frequency. Then there is a controllable power supply which supplies voltage to the DBFS power domain. Okay. Now in the domain which is under the fixed voltage, what basically in this particular example there is a bus to which other blocks in the SoC system on chip can be connected to IOs, etc., etc. In addition, there is a phase clock loop which generates the clock, and then there is another clock generator, which basically what it is just a divider, bunch of dividers which to generate clocks at different frequencies, which are all related by integer ratios. Okay, so there are two clocks. One is a clock to the CPU. There is another clock to the bus. Okay, and presumably there is some intelligence running out here which is not shown explicitly somewhere, which is telling that okay, now reduce the frequency and the voltage, right, or now increase the frequency and the voltage. So that is not being shown out here, but there is something which is running there. For example, another way of doing that is to monitor the number of transactions in the bus per unit interval. Okay, so you can have, that's very straightforward, because whenever you use the bus or the CPU uses the bus, it will raise a certain request signal saying, look, I want to use the bus. And you can have a simple counter which runs, and you can count the number of times the CPU has requested the bus over a particular interval, maybe say 10 milliseconds or 1 second. Then you know how active the CPU is. So based on that, you can kind of decide, look, in the last 10 milliseconds or 1 second or whatever timing interval you're measuring, this is the rate. It's just not using it much, so maybe it's not doing much work. Let me reduce the frequency. Right? It could be based something like that. So again, as I said, there are many different approaches people are using to figure out what should be the target frequency of operation for the next phase of operation of the chip. Okay, now when you do that, what are the various issues in designing such a system and make sure that it works properly? The transitions of voltage frequency should be handled carefully. The interfaces, because you have two different voltage domains, two different timing domains, those interfaces have to be designed carefully. The mapping of frequency to voltage, right? For a given target frequency, what is the right voltage to use such that all my chips will work properly is again something which you have to identify. You have to do that identification, you need to have libraries which will support you, standard cell libraries and libraries of other components. And sometimes you can have certain issues like temperature inversion, where the relationship of delay and voltage is kind of different. I mean, depending on the temperature, right? Because the mobility and threshold voltage behave differently. So if you are operating where you are limited by mobility, that means at very high voltages you are limited by mobility, then as you increase temperature, speed comes down. But at low voltages, if you are limited by threshold voltage, as temperature increases, speed goes up. So the behavior of speed on temperature, speed versus temperature really depends on which voltage you are operating, where you are. So what that means is that sometimes some paths could become critical at some voltages, whereas some other parts could become critical. So that complicates the problem. So what people do is also practical, from a practical commercial implementation. They don't go to very deep voltage scaling. The voltage scaling is kept to be a small amount. Okay. It doesn't mean you shouldn't do it, because these are, how do you make it work across very large voltage ranges? That is kind of something which is an interesting interesting opportunity for figuring out how to do it. Whenever you do these transitions, there are overheads which has to be kept in mind. So you have to kind of make a evaluation: is it worth making the transition, or should I remain there, right? And you have to know when to do the transition, right? When should you actually do it, or what should trigger making that transition, right? So that these two are really the last one especially is related to a system level monitor, which is somehow you have to kind of say, look, I am going to make this transition now, and it really depends specific to the system. Okay, it's not nothing to do with the circuit design, but the system level implementation of this. So let us look at the problem of the interfaces, right? So so here what we have is basically two blocks. There is a CPU which is being generated by standard cell logic. You have the CPU, the code of the CPU in RTL, and you synthesize it. and then that interfaces on one side to the cache, which is really memories, SRAMs, and the other side you have some other logic, probably part of the SoC. The bus will be there, etc. System bus and so on. Now the clock. So you see the boundary of this CPU. You have to have level shifters because the other domains to which it is talking to could be at different voltage domains. So you need to do level shifting, convert the voltage levels between the CPU domain and the other voltage domain. Same for the clocks, because the clocks are generated in a different voltage domain, and when you feed it to the CPU, you have to convert the levels of the clock and feed it in. So you have these level shifters. Now you also have some additional thing called a clamp. Okay. Now the reason you have that is in this CPU you also have the option of power down. In power down, what you do is you just disconnect the power supply to that block. Okay, that is called power gating. The reason you do that is, say you know that I'm not going to use the CPU or some piece of logic, so you stop the clock to that. When I stop the clock, frequency is 0, so I should also get the voltage down to 0. No point having some voltage to that because you have leakage. Whenever you have voltage, you have leakage current. So if you want to reduce the leakage power, you have to disconnect that block from the power supply. Simple way of disconnecting is just you have one more transistor in series, what are called power switches, power gates, power transistors. These are not the power transistors which you might be studying perhaps in your power electronics course. These are just big fat transistors, big white transistors which are in series and connected to the power supply. You just shut them off. You could also have power transistors outside the chip, but the idea is to disconnect them. Now when you disconnect that particular block, okay, what happens to the internal supplies, right? Let us say there is some switch out here which you disconnect the external supply with the internal supply. So this internal power supply voltage, what will happen to that? That will start dropping, right? It's like one big capacitor, no one is holding it because you have leakage happening, like leakage in this, it will slowly discharge that internal power capacitor. When that happens, all the voltages at all the interfaces, these voltages and these voltages will start going down. So you have to be careful because if the other blocks are not power gated, if they are still alive, then at the interface you have a circuit, but the input of the circuit's voltage is slowly creeping down or drooping down and maybe eventually go to 0. So it should not misbehave, and so you need to put clamps, what are called, which holds this, which makes sure that the voltage presented out on the other side of the clamp is fixed. It doesn't get perturbed by this. The simplest, there could be many ways of doing this clamp, but the simplest is, say you have a NAND gate or NOR gate or something. If say one of the inputs, in the case of a NAND gate, right? If the NAND gate, one of the inputs is 0, the output will be VDD no matter what the other input is, right? So even if the other input's voltage is slowly creeping down with time, it doesn't matter, right? The output is held properly at 0. So like that, you have to put some gate to clamp the voltage at the output of the level shifter.
The clamp has on one side of the clamp, maybe if we are having 0 voltage and we are saying that on the other side we should continue to get 1 volt. That means it should be able, it's itself providing 1 volt. So it should be supplied as well. So what will it be supplied?
Exactly. So the question being asked is the clamp voltage. Where is the power supply for the clamp coming? Because we have disconnected if we disconnect the power supply for this block, what happens to the clamp? So the reason you are putting clamps is the clamps are being fed by because you want to connect to another piece of logic which is being supplied by a separate power supply, and that you are not disconnecting. So that is why, because you maybe, for example, the memory, you want to keep the state of the memory, you want to retain the state of the memory. So you might disconnect this but keep that. So in which case you have power available already, that you have to use that VDD from the other side. VDD of the receiving logic domain is what you should actually use. Okay, so this is as far as the voltage. We'll also see actually, but we'll cover that later when we talk about power gating and so on, that sometimes you might want to retain the state even inside this. There might be registers. Because it's a question, you might have multiple power down states. You might be in a standby state then you might be in a hibernate state, you might be in a suspend state. So depending on which state you go deeper and deeper into a lower power mode, right? The ultimate is this, I just disconnect the supply, I'm just nothing is there. But it takes longer to wake up because you have to restore the state, right? So there will be a sequencing by which you have to do this. If you have state and you're going to go into this very deep power down mode where you may be essentially disconnecting the supply, you have to take the state and store it first. Then you go down to the power down mode. Then when you come up, you restore the power and then you have to restore the state and then go back. So going down, coming out, all takes time. Maybe to cut it down, you might have intermediate power down state where what you do is, or to restore it, you might have storage right there which is powered by different supply, where you transfer the internal storage to that, and the internal one is powered down, but the other retains power, and then you can restore it back very quickly. Okay, so now let us look at the problem of timing. So this is as far as the voltage level goes. Okay, so this we have already seen. You're already doing some experiments with the level shifters. Now let us look at the timings, right? So what you have here is a situation where you have this block which is in a separate voltage, dynamic voltage domain, and then you have the rest of the SOC. For example, maybe this is connected to the bus. The name of the bus is AMBA bus. It's just one of the standards used which allow you to hook up multiple peripherals, multiple devices onto this bus. So how do we transfer information across and make sure timing is not violated, right? So here this is kind of this is an approach where you are using synchronous techniques still to transfer. If you recall, in the last semester we studied how you can have asynchronous interfaces, and you can use one of those techniques also, but asynchronous interfaces adds overhead. There's a lot of, there's more circuitry and there is more latency to go across, but you can use that and it will work. But it just adds overhead, especially in a bus to which the CPU is connected to. You kind of want to avoid that because it's just too many cycles are lost. Instead, what is done is the following, where you have your clock to the bus and the CPU clock, which are all synchronous. Okay, that means they are derived from the same PLL, and except that the CPU clock might be some integer multiple of the bus clock, right? Either it's exactly the bus clock or a couple of times, 4 times, etc. Because typically CPUs will be faster than the bus. So they will be aligned, except what you could happen is that there could be clock skew out here. That means even though the frequencies are aligned, the delay relationship, there could be some uncertainty. That is because the CPU clock has to go through these level shifters, right? And as you have different voltage operating points, the delay across the level shifter will also change. That means there is going to be a variable amount of skew between the CPU clock and the bus clock, right? So you could have some skew between the CPU clock and bus clock. So suppose you could characterize that skew, right? You say, look, this is going to be plus minus this skew, maximum skew across all process conditions and across all voltage, scale voltages. Then again, life becomes much simpler to do your design. So what you do is the following. So we have two things you need to reading from the bus. So this is a little bit of a nomenclature. So let me just say, so this reading and writing, see when I'm, so this is, I'll just, to make it simpler, I'll just putting data onto the bus. Okay, the CPU wants to put data onto the bus. So, so basically now what happens is that the CPU wants to put data. So what you do here is that you have these latches. No, actually this one is CPU reads data from the bus. Okay, I am myself confused out here. CPU reads data. From the bus. Okay, so so here what happens is that on the positive edge of the bus clock, So some person, some device out here is transferring data onto the CPU. So that puts out the data onto this bus, common bus. Now you have these latches, low phase latches. That means the latches are open when this edge clock is low. They're transparent. Okay. Whereas they hold the data when the edge clock is high. Now the thing is that the CPU clock can come little early or it can come pretty late, a little late by the skew amount. The skew is plus minus t skew. So then if the CPU clock comes a little late, this latch here is opaque in this time, right? It is holding the data for you. So it's still okay, you can pick up the data. The new data which has been put by the bus, the guy on the bus will not come and mess up this data because this latch is holding the old data, it can pick it up. So that helps that. Now if the CPU clock comes a little early, then what you have to ensure is that when the person who is transmitting the data to the CPU, that data when it comes out from that block and goes to the bus and comes here, it should satisfy the timing which is TH clock minus T skew. Right? If you can guarantee that, then you're still okay. Then the CPU clock will be able to pick up that data properly. So what this means is that when you do your synthesis of the bus and everything else, you have to give this delay constraint to the synthesis tool, so that when it synthesizes, you say this constraint that my delay, I synthesize to this delay. So this way you are able to pick up the data properly. The CPU is able to pick up the data properly no matter whether the skew is plus or minus, except as a designer you have to ensure that the skew is bounded. That means you have to characterize this level shifter and design it so that across the voltage scale voltages and across process conditions and temperature, etc., there is a skew number you adhere to, right? And that number then you use when you are doing the synthesis of the rest of the system, especially the bus. So when I want to CPU writes data onto the bus. This one is CPU reads data from the bus, CPU writes data onto the bus. So here now what happens is that instead of low phase he has high phase. That means it's transparent in here. What is the benefit? Because when the CPU sends out the data, if my bus is my CPU clock is delayed, it is still okay because my bus clock is the latch is transparent out here, so it will still flow through across. Okay, and so that means when that data flows through, it has to be captured by the next rising edge of edge clock. That means this whole system again should be synthesized such that the data when it comes out of this, when it flows through this latch, comes out, goes into the bus, there could be many things on the bus, no matter who is getting the data should be able to, the timing should be such that that delay should be less than TH clock minus T skew CPU clock, same. Of course, now if the CPU comes a little earlier, there is no problem because it just comes and it waits, and then this guy takes it up and you cannot go through. Of course, you don't want perhaps, so this is also, there are certain additional constraints which come up here. Maybe you don't want your CPU clock let me go down a little bit, look at the waveform, yeah. So you don't want, if the CPU clock comes a little earlier, it gives out the data, which is fine, it remains here till the next edge of the bus takes it and you can, it can be consumed. Okay. Now what I was going to say was that maybe the next edge of the CPU should not give out the new data. That will basically not happen because of the way the bus protocols work. You give out the data, you wait for an acknowledgement. Again, it depends, right, what the protocol is. If it's like that kind of a system, then you won't have that problem. If not, you will have to ensure that you have to take that into account when you're doing your design, right? Any questions on this? So this handling of passing the data from one domain to another domain, right? Another name for that is what is retiming, because you're retiming the data. The data is synchronous to one clock domain. Now it is going and becoming synchronous to another clock domain. So that is retiming. So you can also do that retiming using registers, because sometimes with latches, as I said, it is trickier to deal and do timing analysis. So you can do it with registers. So here what is done is basically you don't have latches, but you just have registers. Okay, so how does this work? Here what is basically done is that they, in this case, they ensure that the CPU clock is always earlier than the bus clock. When they are doing the design and generating the clock tree and all that, they ensure that no matter what, even after going through the level shifter, the CPU clock always, despite the worst case skew, etc., no matter what voltage level is, it comes ahead compared to the edge clock. These are additional constraints you put. The reason they put these constraints is that in the design of the clock tree is that then it makes their analysis and rest of the design simpler. Okay, so that's basically the approach they take in this example. So your CPU clock comes earlier, and so here we are talking of looking at timing to write into the bus. Okay, your CPU clock puts data, and then your bus clock picks up that data. And what is being given, as a designer of the clock tree, you have to ensure that there is enough separation between the CPU clock and the edge clock, so that you don't violate the setup requirements of this register which is being triggered by the edge clock. Right? If you can guarantee that, then this will again work properly. And similarly, when I want to send, and this CPU, when I'm sending data from the bus into the CPU, I have to ensure that the delay of the data from the sender going through the bus and being captured by the CPU is less than the minimum delay between these two edges. Okay, so that is the constraint I have to put on my synthesis when I synthesize it. That way I will again ensure that I don't violate the timing. So now I'll just introduce this, but we'll go again in more detail in the next class. So that was dynamic voltage scaling, where that is basically the interface issues. How do you handle the different timing and voltage domains? Whether you do dynamic or voltage, you still need to do that. Now the thing with the dynamic was, as I said, DBFS, you have some fixed table which you have to pre-characterize during design time and then use that table, F2V mapping. Can we per chip figure out what is the actual F2V mapping for that chip? Right? If you can do that, then for per chip you can adjust. That is what is called adaptive voltage scaling, and that is basically done by adding an additional hardware monitor out here called performance monitor. Now, what is that performance monitor? How you design it? We'll kind of take it up in the next lecture. But really, that helps the system to know if I want a desired frequency, what should be the voltage, and then the system goes and sets it to that voltage. So I can get additional power savings beyond just dBFS. So this we'll look at in the next class. So you can read up chapter 10, which actually goes through a case study where they have taken actual SOC and applied both dBFS and adaptive voltage scaling. Of course, that chapter doesn't go into detail of how the performance monitor has been actually implemented. For that, we'll have to look at certain other references. So that we'll again do that in the next class and the following classes. Any other questions before? Okay.